Hello, and welcome to the first demonstration of the CANDO, Computer-Aided Nanomaterial Design and Optimization Computing Platform. CANDO is combined with JupyterLab. JupyterLab allows us to have a web-based or cloud-based interface to run the CANDO computing environment. This video is presented by ThirdLaw Technologies, LLC. This is the first demonstration of the CANDO software environment on this channel, and there will be several other demonstrations of the software, the platform, how we're using CANDO, many other demos to come. So CANDO is a complete computational computing environment, a computing environment, really. It's for computational chemists as well as bench chemists. We combine the capabilities primarily of AMBER molecular dynamics systems, LEAP and antichamber and such. We support several different types of force fields, not just the AMBER force field. We support the Open Initiative force fields as well. Molecular modeling and visualization capabilities are built into the platform using widgets in JupyterLab. JupyterLab is an extremely flexible, portable environment. It lets us run CANDO on a server halfway across the world and access it via a web browser. We're built on a powerful programming language for quick development and custom workflows. The CANDO software environment can be found within a Docker image, and you can run everything that I will show you today within that Docker image. It can be found on Docker Hub at ThirdLaw/CANDO. You can run with an associated dataset if you'd like. That can be found at the GitHub for FEP benchmarks. These benchmarks are free energy perturbation benchmarks calculated using the Schrödinger software FEP+. So I have the CANDO environment set up on my machine, my local machine, which is a 4-core laptop. I have the browser open here, and on the left you can see several demos that we have. In this demonstration, I'll be showing you a thermodynamic integration demo. So once you open the notebook, you can see several different things. So there's a few links here for CANDO that will take you to the GitHub. This is where you can download the actual source code for CANDO and install it on your system. There's a link to AMBER if you're not familiar with AMBER MD. It will show you everything that you need to know, manuals, how you can download AMBER and use it. And then you can find a little bit more about ThirdLaw Technologies. We're not just a software company. We have an associated chemistry division called ThirdLaw Molecular, where we do bench chemistry. And there's several other videos of our founder talking about the computing platform. Okay, so at the very top of the notebook, you'll see, in order to run this, what we want to do is go to Run and then Run All Cells. That will set up the notebook for us to start doing some calculation. So we go up here to Run All Cells. And it'll just take a minute for CANDO to start up the notebook and start filling in these different things. So this demonstration will be surrounded around thermodynamic integration, transforming one molecule into another molecule and calculating the associated relative free energy difference between those two molecules. Now we can do that not just on a singular scale, but on the large scale using the lead optimization mapper code, actually a new implementation of the lead optimization or LOMAP code within CANDO itself. So in step one, what we basically need to do is we need to create a thermodynamic integration instance for us to set up our calculations. Now we have a workspace widget here where you can set up a calculation and then save that calculation and come back to it, rerun it, change it, rerun it again. Or you can create a new calculation. That's what we'll do, and we'll call it workspace 1. We'll come down here to step 2. Now, what we want to do is we want to load a Pdb file. This is our receptor file. So we'll come in here and we'll start looking for our Pdb. So I have the FEP benchmark Git here, and I'm going to go into the EG5 example, and I have a PDB prepared. And it just takes a minute to load up the NGL window. This is a regular NGL view window embedded into this notebook, and we can go full screen if we like. There's a few associated ligands with this this protein, but you can view the protein very nicely. Okay, step 3, what we need to do is load our ligands. So in the FEP benchmark example, inside the EG5 folder, we have a couple of different ligand files that have about 28 ligands inside. You can load it SDF, mol2, it's your preference, your choice, but all formats are acceptable. And it just takes a minute to load the ligands here. Now we'll see some things down here is happening. This table is populating, but if we come up here where we loaded our ligands, now we can see our ligands in the window. We can select them and look at them individually here. We can scroll through them very quickly. And then on the right-hand side, we can see another NGL window where we see the receptor and the ligand docked inside, and it's a completely independent cell. So we can rotate the receptor. We can change the formatting if you like surface representation of the receptor. And you can see that ligand embedded in that pocket very nicely. We can turn the receptor off. We can look at the ligand. Now, let me move the window over. This window here has a few different features. So let's say we docked this molecule, or we created this molecule and docked it into the binding site of a receptor. And we saw some clashes up here. What we can do is choose a bond where a dihedral will be chosen, and we can actually rotate using this slider. We can actually rotate that about that dihedral angle however we would like. Okay, we can come here and do the same thing. Let's say there's a clash there and we just need a little bit of a tweak. Whoops. Click on this bond, it recenters. We just need a little bit of a tweak. Okay, that looks good. Okay, now we can minimize that structure using the minimize button, and it will minimize that structure quite quickly. Now let's say, okay, I want to have actually a different conformation. Let's jostle all the atoms and bring everything back and have a completely different setup. So we jostle all the atoms and we come back to a minimum. Then we can even minimize that, and we're pretty close to the minimum after the jostle. Okay, and we can bring the receptor back. See how things are looking. Let's choose something a little bit more informative. Let's choose ribbon. And everything is looking good. Okay, let's move on to the next step. So we have all of our ligands here. Like I said, about 28 ligands have been loaded. Now we can come down here and we can see all of our ligands are in this table. And here you can down select the ligand. You can select them all. You can select none. So what I'm going to do is I'm going to, let's say, well, I don't want some of these ligands. They kind of all look the same. Let me click off some of these ligands. Okay, now let's go down here and let's make our calculation map. So here is where we'll be calculating our similarities using the lead optimization mapper technique. Now, as I said, this isn't LowMap itself. I'm going to start the task. It takes a little while to generate. This isn't the exact LowMap implementation. We actually use LowMap as a guide to design our own lead optimization mapper where we calculate similarities using MCS, and it's all built around graph theory. So I've chosen probably around 20 molecules or so. They're all listed here. And what it's doing now is calculating all the molecular similarities and building the graph for the comparison of each molecule that will be calculated over the thermodynamic integration calculation. We have a progress bar here, so you know how long this is taking. Again, this is on my my 4-core laptop, so it's not super fast like on an HPC. And what we'll see pop up is a window showing the complete calculation, all mapped out. This algorithm takes into consideration every molecule is contained within a thermodynamic cycle. So we are preserving the efficiency of the calculation, and we're not wasting time doing various calculations. Okay, so we have a map here. We can change the way this map looks any way we like. There's different ways, however you would like to look at the map. If we zoom in a little bit, I can actually zoom in using the scroll wheel. And what I can do is, okay, well, I see these two molecules are relatively similar. They have a 0.6 similarity score. If I click on this edge, I can see, oh, that one actually goes through. Okay, so I can see, okay, there's a common core here, the common core here, and these are the atoms that will actually be in the soft core transformation. These will be, the core will be in a linear transformation of the thermodynamic integration calculation, and the highlighted atoms will actually be in the soft core. And you can see those transformations very clearly. So the next thing that we would do is come down here and we would set up our parameters. And those of you that have used Amber in the past, you will recognize these parameters as standard input parameters. So here you can choose the size of your water box. You can set your calculation limits however you want, however long you would like to run your various calculations, your heating, your constant pressure calculations, and there's various other parameters for the soft core potentials. So let's just say, okay, I would like to use the default settings here. I can come down here and I can choose a job name. Let's call it TI Run 1. And here you have a choice to do a single stage calculation or a 3-stage calculation. Now the 3-stage calculation within Amber will do a decharge, then it will do the van der Waals non-bonded calculation, and then it will recharge the molecules and do the recharge calculation. Single stage doesn't do the decharge recharge, only does the van der Waals non-bonded calculation. But you have the ability to choose between what type of calculation that you would like to do. And then we're going to write out our jobs. And it's going to do a few things. It's going to write all the files to do the thermodynamic integration calculation. It's going to create the job tree and connect all those jobs to run the TI calculation to completion with basically no input from the user. So it's writing everything. Okay, successful. So we can come here to our terminal and it writes it into your home directory, into the jobs folder. So let's see. Yes, so here is our TI Run 1 directory. So let's move into that directory. And each one of these directories is a transformation. So each one of these is an edge that will be calculated to get a relative binding free energy for all these edges. But basically everything is set up now here for me to run the calculation. Let's move into one of these directories so you can see how it's set up. So let's move into this top edge directory here. And you'll see that we have a setup for ligand and for the complex. Let's move into the ligand and let's look at one of these files, right? This is a typical Amber file, Amber input file. So let's look at the pressure.